Hey, stop! Do you know that chocolate might come with a side of poison?
Huh? Excuse me?
Actually, cocoa beans are heavily sprayed with pesticide to fight pests. And because cocoa is so fatty, those toxic chemicals get trapped inside. It's a nightmare to detect.
Oh, you're saying this is toxic?
Not necessarily, but to know for sure, you need analytical chemistry. I actually just finished a study. Let me show you the slides.
Hi everyone, my name is Lin Jingyan, EGE 2409045, and our group will be presenting the article's title Crochets Combined with a Low Temperature Party Tuning and GCMC as an Analytical Strategy for the Determination of Multi-Class Pesticide Residues to Cocoa Beans.
Cocoa is a massive economic crop for Brazil, but farmers face challenges from witches-borne disease, which can destroy up to 90% of yields. To save their crops, producers rely on agrochemicals classified as persistent organic pollutants. These are linked to several health risks, including cancer and Parkinson's disease. However, monitoring this is difficult because cocoa is a complex matrix that rich in lipids and interferes with standard lab instruments. While the industrial standard catches method is effective, but it requires laborious cleaning up. To solve this, we use low temperature partitioning, which frees the sample to effectively remove those interference. Based on those challenges, our study has four main objectives, but our main purpose is to apply this validated procedure of determination of 16 multi-class pesticide residue to investigate the occurrence of this pesticide contaminant in real commercial cocoa samples.
First, dry cocoa beans were ground into a fine homogeneous powder and stored at negative 18 degrees Celsius to prevent analyte degradation. For extraction, 2 grams of cocoa powder were weighed into a 50 ml centrifugal tube. Next, culture extraction was performed. The sample was hydrated with 2 ml of water to enhance extraction efficiency, followed by the addition of 8 ml of acetonitrile as the extraction solvents. A salt mixture of sodium chloride and anhydrous sodium sulfate in a 1:1 ratio was added to induce phase separation through the salting out effect. The mixture was vortexed for 3 minutes and then centrifuged for 10 minutes to separate the acetonitrile layers containing the pesticides. For sample cleanup, dispersive solid phase extraction was carried out. 6 ml of supernatant were transferred to a tube containing primary, secondary amide solvents. This step removed polar metric interference such as sugar, organic acids, fatty acids, and pigments. The mixture was vortexed and centrifuged to obtain a purified extract. The extract then underwent low temperature partitioning by freezing at negative 12 degrees Celsius for 24 hours. This allowed residual water and the impurities to solidify, while the pesticides remain dissolved in the acetonitrile. Finally, the purified extract was filtered and analyzed using GCMS in the selected ion monitoring modes, providing high sensitivity and selectivity for pesticide detection.
Results and discussion. So first we optimized the extraction. We found that water volume was the most significant variable and PSA sorbent gave us the cleanest extract. We also compared the freezing temperatures, and surprisingly, the standard freezer at negative 12 degrees, those orange bars, actually gave us much better signals than the ultra freezer at negative 80 degrees. Slower cooling actually helped the pesticides to separate from the fats more effectively. Next, we validate this method. So all 15 pesticides has achieved R-square more than 0.9985. And the logs range from 13.9 microgram per kg to 23.1 microgram per kg. Now this is very sensitive. Our recovery rates were within 62.4 to 120%. So this method met international standards with RSD values below 21%. But the biggest challenge was the matrix effect. Every single pesticide shows signal enhancements. Looking at the gap between these lines, that is the signal boost caused by cocoa lipids blocking active sites in the injector. The worst case was cyproconazole, which was boosted by a factor of 20.5. We had to use matrix match calibration to close this gap to ensure a more quantitative accuracy. And finally, real sample analysis. 15 commercial cocoa samples from Bahia and Pará were analyzed in triplicate. So permethrin was detected in 4 samples at concentration ranging from 17.1 to 49.6 microgram per kilogram. So look closely at peak 17 and 18. This is permethrin, which we found in 4 samples. So we also detected levels of molinate below the limit of quantification in 3 other samples. So the good news is all levels were below the European safety limit of 100 microgram per kilogram. So scientifically speaking, the chocolate is safe.
Now moving on to our final conclusion. First, regarding the automation of the method, we discovered that using a conventional freezer at negative 12 degrees Celsius was actually superior to using an ultra freezer at negative 80 degrees Celsius. As you can see in figure 3, the conventional freezer yielded higher recovery rate. This is because the slower freezing rate allowed the pesticide more time to separate from the water phase before the mixtures turn to solid ice. The overall protocol proved to be highly robust. By combining cultures with low temperature partitioning, we successfully removed complex interference like lipid and pigment without the need for expensive commercial solvents. Finally, regarding food safety, when we test real cocoa sample, we detected permethrin in 4 samples. However, all concentrations were well below the European Union safety limits. This confirms that our proposed method is not only cost-effective and green, but also a reliable tool for the cocoa industry.
So, without pesticide, it is safe to consume?
Exactly. Our method proved that while residue exists, this batch is compliant with the safety regulations.
In that case,
Thank you for that.